Okay, Bismillah ar-Rahman ar-Rahim. So we started talking about. So we started talking about the local wireless local area networks and the architecture of this standard. We did not talk about how we can provide quality of service yet, but we talked about one of the issues, which is co-location or coexistence of multiple basic service sets or multiple cells. They can coexist at the same location, and in that case we have to coordinate what channels are being used by each cell. We can use in the physical layer some technologies to provide some isolation between these cells. One of them, as we said, is frequency hopping spread spectrum, where we can change the frequency used by each channel randomly in a short time frame, which will allow this cell to use a specific frequency for a short period of time, and then we start hopping between these frequencies to facilitate the interference between two co-located cells. So the way that we organize these channels depends on what variation of the standards that we're talking about. We covered multiple of these variations. We talked about 802.11b. We said that this is the baseline standards, which works in 2.4 gigahertz. And we also talked about 802.11g, which tries to use the same architecture of the B, but with higher throughput or higher data rates, which can go up to 54 megabits or 54 megabits per second. We also talked about 802.11a, which tries to resolve the issue of interference in the ISM band by using a totally different spectrum in 5 gigahertz. Okay? So regarding the channel for co-location, to facilitate the co-location, the 802.11b uses a total spectrum of close to 100 megahertz. Okay? So the total spectrum is 100 megahertz, and it tries to divide this total spectrum into sub-channels. Okay? Usually, each channel is around 20 to 22 megahertz, which means that maximum, we can have 4 channels which are separate from each other, right? Because if we, on the average, if each channel can exist in a bandwidth of 25, assuming that we have guard bands, okay, so between each 2 channels we need to have guard bands. So each channel will occupy, okay, a spectrum or a bandwidth of 25 megahertz. Okay, so maximum we can support 4 channels. However, the standards define 2 modes. One mode is that we use 3, we call them non-overlapping channels, okay, which occupy a range which is slightly less than 1 megahertz. Okay, 100 megahertz, sorry. Okay, so we can define 3 non-overlapping channels, which is channel 1, channel 6, and channel 11. Okay, another mode which uses 6 overlapping channels. As we can see here, these channels are overlapping because to fit 6 sub-channels, each with around 25 megahertz with the guard bands. So this means that we have to have these channels overlapping with each other. Okay? When we have 2 or 3 of these channels overlapping, this means that they are interfering with each other. Okay? Which makes the problem of allocating a certain channel interesting, because then we can, if we have multiple of these wireless LANs or BSSs, are co-located in a in a small geographical area, this means that you will have a different level of interference depending on your location or the location of this wireless LAN. Okay, there is a special software that you can use, because actually, even if you use the channel number as O2, that's usually not very accurate in selecting the best channel with least amount of interference. So some developers, they actually can use a special software which you can run on a cell phone or on a laptop, and you can just scan all the existing wireless LANs in a special location, okay? And it displays it for you in a frequency spectrum manner, which means that you can detect that this wireless channel, or sorry, this wireless LAN has this ID, and it runs on this frequency range. This wireless LAN runs in this frequency range. So you can do this simple measurement to know how many channels are occupying certain frequency range, and based on that, you can select a frequency range that does not interfere with any of them. Okay? All right, so in any case, the standards actually define 3 non-overlapping channels or 6 overlapping channels. In fact, 802.11g defines 11 overlapping channels, because as we can see, channel 1 and channel 11. So you can have 11 overlapping channels, in which case the spectrum is squeezed with more subchannels. Okay? So as you can see here, it starts from 2.4, which is the carrier frequency for 802.11b and g. And then from 2.4, you have multiple channels depending on whether you're working on a non-overlapping mode or overlapping mode. Okay? So this is what the North American standards actually define. There is another way of defining these channels in the 5 gigahertz range, which is valid for 802.11a. So the 802.11a defines these channels from 5 gigahertz, and in fact it starts from 5.1, and again it defines a range of frequency of close to 100 megahertz, and it actually divides that into 12 different subchannels. Okay, and these channels are non-overlapping, in which case the channel bandwidth itself is smaller than 25 megahertz. And what happens here is that these subchannels are divided into 3 categories. There is one category called lower UNII, which is this range from this channel to this channel. Okay, so it's actually so these 4 channels basically. Okay, and so this is the lower, and here there is the middle, and this is the upper. So each of these are subchannel groups. Okay, and each of these groups are categorized in one of these categories. So there is the lower, the middle, the upper, and each of these categories are subdivided into 4 sub-channels. Okay. So any questions so far? So whether you are working in the 5 gigahertz range or the 2.4 giga range, you can, whether you're using any of these standards, so you can use these channels at any point in time. Also using FHSS, or frequency hopping spread spectrum, you can also jump between these channels at any point in time. Okay? Any questions? So this is how we do the co-location. So regarding the 802.11 layer stack, as we know, there is the sub-layer on top of this, which is the logical link control, which is also part of the data link layer. So the data link layer itself is divided into two sub-layers, but this logical link control is not part of the 802.11 standard. And again, why? Because it's totally medium independent, and therefore it's common between all the 802 families. So 802.3, 802.11, 802.15, 802.16, they all use the same logical link control. So that's why they separated this logical link control in a different standard, and then each family of the 802 defines a separate standards, whether it's .11 or .3 or .15 or .16 and so on. So each of these standards, they define the MAC sublayer as part of the data link layer and the physical layer. Okay, so so in that case, there is between each of these sublayers, we have an interface point, or what we call service access point. The service access point acts as an interface to any sublayer. It's like when you have a code, okay, and then you divide this code into sub-functions that each function it calls the one after it. So so you have an intensive amount of code, and the interface is actually the name and the list of parameters for a specific function. So each service access point defines what APIs you can call from this sublayer. And these APIs are called by the above sublayer. Okay? So the above sublayer, when it tries to send anything to this sublayer, it uses the service access point set of APIs, which can trigger a certain functionality. Of course, the actual body of the function, which is the procedure or the algorithm, is part of this sublayer. Okay. So as we know, roughly speaking, the MAC sublayer defines the medium access control, which is the sublayer which is responsible for maintaining the control how to access this particular medium. Whether this medium is, in our case here, it's wireless, and in that case, we have to perform carrier sense multiple access with collision avoidance. Okay, so with collision avoidance. So that's what this sublayer actually performs. Then we go through the physical layer service access point, and the first thing we hit here is what we call, actually this is PLCP. It's called Physical Layer Convergence Protocol. Physical Layer Convergence Protocol. So what this layer, again roughly speaking, what this layer does is that, if you remember in 455, we said that there is a frame, right, which is defined as protocol data unit in the data link layer, which includes the header, the data, and then the trailer, right? But there is a specific fields, or a specific set of fields, which is what we call preamble. If you remember, as part of the Ethernet standards and also as part of 802.11 standards, there is the preamble, and we said that the preamble defines the beginning or the start of a frame, right? In fact, the physical layer convergence protocol, it does that. It generates a preamble as a signal to indicate to the receiver that, you know, this is a start of a new frame. This is the end of the end of that frame, and you should wait for another preamble for the start of a new frame, and so on. So this sublayer is actually an interface between the MAC layer and the what we call the physical layer medium dependent sublayer. Medium dependent sublayer here, it's the layer that heavily depends on the type of medium, and this is the layer that actually generates the signal depending on the type of the medium. So if we're talking here about wireless, this is the actual sublayer that generates a signal, an analog signal, and the RF signal, okay, that can work in 2.4 gigahertz or 5 gigahertz, and which channel, what frequency it uses. So it actually controls the carrier frequency and the shape of the analog signal that it should send on a specific frequency to utilize a specific channel. So in other words, all the signaling, okay, is actually performed by this sublayer. Okay, but this layer, it does the encoding part and the start and the stop of a new of each frame. So they call it convergence layer because it actually tries to customize the frame, okay, into a format which can later on be transmitted by this sublayer. So it tries to regenerate the frame in a generic format, okay, that can be then generated as a signal to be transmitted over the specific medium. Okay? So this is just an overview about the functionality of each layer. Of course, we'll go into a little bit of details about specifically the MAC layer. We'll spend a fair amount of time on that. These sublayers, they are management entities. And by management entities here, these layers, they actually maintain the control and the measurements that have to be done within each layer. So if I want to, for example, control what channel I use, or to get some information about a specific channel, what level of interference, what is the signal strength, things like that. So whether I need to get the status of a particular channel, or I need to control that I want to use this channel at this point in time. So there is a layer here which we call it the management plane. The management plane, as you can see, it's common for all the standard. There's one plane which is called the management entity, and this management entity then can communicate with a layer-specific management entity, whether the MAC sublayer management entity or the physical sublayer management entity. So this control plane, okay, this management and control plane, it actually can communicate with each layer through these entities. And the management entity, as I said, is used to configure and get the status of some specific parameters in each layer. For example, if I want to measure the status of a certain channel, what kind of interference I'm actually experiencing at this point in time in this particular channel, then the station management entity will send to the physical layer management entity to get the status of a particular channel. Okay. If I want to set the channel number, then it sends a command to this management entity to set the channel number to channel 6, for example, which means that this PMD sublayer will now use an analog signal in this particular. Okay, so any questions? So this is the sort of the layer stack. So this is the interesting thing is that 802.11, the MAC architecture defines two operation modes. Okay, defines two operation modes, and from here we'll start to see some techniques and mechanisms which we can use to provide service differentiation and quality of service. So there is the mode of operation, which is what we call point coordination function. and there is distributed coordination function. So we'll talk about the differences between each of these operation modes. Many of us don't know anything about the point coordination function. DCF is, you have some idea about DCF because this is where all the sigma CA is actually run. Okay, so DCF is basically sigma CA, okay, but with some extra things that we will talk about today. PCF, well, as we have talked about before, DCF itself, it's really challenging to provide any service guarantees using DCF, right? Because we don't have control whether there is a collision or not, right? We will try to avoid it, but we will never eliminate it, right? We using DCF, by default, we cannot provide any service differentiation. So we cannot actually give certain priorities or certain differentiation for a specific node, okay? So that's why the standard defines an optional operating mode, which is what we call PCF. PCF uses polling, okay? So polling is collision free or collision based? Collision free. So polling is by default collision free. So when we have a collision free environment, as we have discussed before, one possibility is to control the polling sequence, in which case we can provide a service differentiation. Okay, so this mode of operation allows us to provide, even in some cases, quantitative quality of service, right? Because if we can control the polling sequence and give specific amount of resources to each node, we can sort of guarantee certain quantitative quality of service to some nodes. Here, we cannot do any level of service differentiation, but as we will see later, 802.11e tries to override that and enhance this mode to provide some qualitative service. Okay, so that's in a nutshell how these modes operate. So we have one frame, which is what we call contention-free period. Okay, it's a macro frame, or it's a very large frame. This frame, in that case, is like few seconds, and this frame is then subdivided into point coordination function and DCF. So you can actually, this boundary, you can move it back and forth as you wish. Okay. In fact, PCF is totally optional. So the standard defines the fact that PCF is totally optional, which means that this period of PCF could be 0. Okay, but you have to have DCF. So by default, the standard actually supports distributed coordination function, and the access point usually sends a beacon. A beacon is different than any other thing that we have. A beacon is a start of a macro frame, okay, and then it ends that with another beacon, and usually this beacon actually defines the duration of PCF and DCF. It provides how much it divides the frame into PCF versus DCF. So you can change the how you divide the frame at any point in time. So the access point tells all the nodes how it divides the frame. Okay? So now, what we are used to, or what we are familiar with, is DCF, and DCF uses sigma CA, so we're familiar a little bit with how sigma CA works. In that case, the name itself, distributed coordination, suggests the fact that there is no centralized controller. Okay, so the only thing that the access point controls is to identify when the DCF period starts. Okay? So during this period, what happens is that every node will contend. We say that the node contends on the channel. Okay? Which is what we call a contention-based. So each node will, before it sends, it will sense whether any other node is sending, and if it finds that the channel is free, then it sends. Actually, what the standard actually defines is that when the node finds that the medium is free, it doesn't send right away. So I have to wait for a certain period of time. So DCF is implemented by default in all PSSs. Okay, so by default it's mandatory and it has to be implemented in all PSSs. As we said, PCF is optional. So that's the procedure for SYSMA CA, and I assume that we are familiar with that, except with certain, maybe some of these signals we're not familiar with, and then we will talk about why we need to perform these signals. Okay, so we have, the standard actually defines multiple levels to try to avoid the collision. And most of these levels do not exist in Ethernet because of the fact that we can easily detect, okay, collision. But here we cannot. And it's unfortunate because in order to avoid collision, we have to do, several levels of precautions. Okay, so that's what we need to talk about. So at the beginning, we perform the persistence strategy. Persistence strategy is that we need to sense the channel. Why we call it persistence strategy here? Because even there are different strategies for how to sense the channel. Because I can sense the channel continuously. Okay, I keep sensing the channel until I find it empty. Okay, so this consumes energy, right? Or there is another strategy that suggests, instead of sensing continuously, I will sense, okay, and then I will wait for a little bit, and then I will sense, and then I will wait. So there is some idle periods between them. So this actually saves on the amount of energy. But the cost is maybe I will lose some opportunities that the channel is free, and because I waited for a long period of time, I did not capture this opportunity. So it's a trade-off, and that's why we call it here persistence strategy. How persistent you are in sensing the channel. Okay, so there are different strategies in how to sense the channel. Okay, so once you do the persistence strategy, and assuming that the outcome is that the channel is free, you don't send right away. You have to wait for a certain period of time. We call it the DIFS, interframe spacing. Okay, so this is stands for DCF interframe spacing. Okay, so the interframe spacing is actually a gap of time, which allows the fact that if two nodes are sensing the channel, close to each other, then when they wait, they will not try to access the channel at the same time. Okay, so after the DIFS, you have to sense again. Okay, so in order to access the channel, you have to wait for a full period of time of DIFS, given that no one will try to access during this time. So this is a second level of trying to avoid the collision. So in order for you to access the channel, or to gain access to the channel has to be free for a period of time of DIFS. Okay? So when you find that the channel is idle, you wait for DIFS and then you sense again. If the channel is still idle, then and only then you can try to access the channel.
This is
Yes, this is fixed. So this is a good point. If this is fixed, then there is no service differentiation. Okay? Because if all the nodes have to wait for DIFS, and this is fixed, this means that there is no distinction between these nodes in accessing the channel. If we can change DIFS, then we can provide some service differentiation. And that's what 802.11e tries to do. We'll talk about that. Okay, so after DIFS, the channel is still idle. Okay, so a third level of trying to avoid the collision is to announce to everyone that you need to send data. Okay, which is what we call request to send. So you send a small signal, a very small short period signal called request to send. So this request to send is a very short period signal. Okay? In this signal, you will give the duration of the data that you want to send. Okay? So everybody will, or hopefully some nodes will receive this RTS announcement. Then what they will do is that they know that I'm trying to send. Okay? Because again, maybe two nodes are trying to send at the same time, and they try to, after DIFS, they try to send data. If they send data, then the collision will happen. But remember, collision with data is very expensive, right? Because we cannot detect the collision. Once two nodes tries to send data at the same time, the data period is very long. Okay, so the wasted time is very expensive. If the collision happens in RTS, it's fine. It's not that expensive because RTS is very small signal. Okay, type. How do I know that there was a collision in RTS? I will wait for a certain time, and then the receiver, only the node that I'm trying to send to, will send another signal called clear to send. Clear to send. I'm expecting your transmission. So if two nodes try to send RTS at the same time, the CTS will not be received, in which case, خلاص, I will wait for a very short period of time, and then خلاص, I will have to go back and I will have to perform again sensing and so on. Okay, so if I receive CTS, then and only then I will have to wait for this time, not DIFS, it's called short interframe spacing. The short interframe spacing is a very short period of time which is only used to calibrate the hardware and also change the hardware from sending CTS into receiving, because the hardware itself requires a little bit of time to change it from sending to receiving. Okay, so SIFS is a very short period of time. Then the sender will send the data. So now we have done 3 levels of trying to avoid the collision. Okay, but again, this will reduce the probability, but will not make it 0. Will never make it 0. Okay, so send the frame and then set a timer to receive the acknowledgement. So in which case, in order to send one frame, we need 4 different control signals, and including the data itself, okay, to be sent. So RTS, CTS, data, acknowledgement. This is only to send one single piece of data. Okay, all the RTS, CTS, and acknowledgement, this is done to try to avoid or to facilitate the fact that we do not detect the collision. Because we do not detect the collision, we have to try to avoid it as much as possible. And the only indication for us that there was a collision or there was any type of error is not by receiving the acknowledgement. Okay? So If I receive the acknowledgement, then everything is fine. Otherwise, we will perform the backoff. And as we said before, the backoff is another phase where I can provide some service differentiation as well. The standard here defines random backoff. So each node will generate a random number and will decide to wait for a certain period of time, and then it will try to access the channel again. And by random, we mean that we try to generate a different time, but on the average, on a long period of time, we will be fair. Okay, so that's what random here tries to achieve. Tries to achieve different, but fair along a big time horizon. Okay, so maybe you have studied this before in 455 or Network 2, but maybe RTS and CTS, some of you are not familiar with them. Okay, so that's this is the sequence in a timely manner. So the source here waits for a DIFS if it finds that the medium is idle. Then it sends RTS. Okay, here the destination will have to wait for a short period of time. So any switching from sending to receiving here, you will find that you have to wait for SIFS. Okay, but DIFS is separate from this. DIFS is a little bit longer. So DIFS is a little bit longer, and it's to facilitate the fact that try to do some again collision avoidance by waiting for a certain period of time to make sure that the channel will stay idle during all this time. If the channel stays idle for all this time, this means that it's for sure idle, and then you can access the channel by sending RTS. Then the destination will send CTS, and then again to switch from sending to receiving, you have to wait for SIFS, and then you send the data. The data, of course, is very long in terms of time. Okay, it's very long time duration. The problem with the data is that even if there is an overlap of 1 nanosecond, yani two nodes send data, and there is only overlap of 1 nanosecond between the two data, all the two frames are gone. Okay, so that's why we need to have several levels of collision avoidance to try to minimize or to eliminate any kind of overlap between the two nodes sending data. And then the acknowledgement. So only if this sequence is working fine, then the frame is sent successfully. The only thing we need to talk about here is that there is another thing called network allocation vector. NAV here is a concept where the nodes that are not involved in the transmission, they will have to experience what we call NAV. NAV يعني I'm not part of this transmission, but I know about it. Okay, so NAV here is done when a node receives any of these frames. Okay, and that's why we try to have different frames to inform as many nodes as possible that I'm trying to send. When more and more nodes are informed, okay, they will refrain from interfering with this transmission. So remember that some nodes, they may actually listen to RTS. Okay, so these nodes at this point in time will perform NAV. They know that a node is trying to send, so they will go into a NAV period where in the RTS, again, you have to report the duration of your data. So so any node that listens to RTS, it knows that the transmission will start from here and it will end here. So it knows exactly the time duration of all the transmission. Okay? And this node will go into NAV. Maybe some nodes in the network will not listen to RTS, in which case they may try to interfere by sending RTS, okay, which may collide. It may actually perform some collision. So hopefully, when I send CTS, remember, RTS is sent from the source to the destination. The destination is sending CTS. So maybe in the some nodes are not in the range of the source, but they are in the range of the destination. That's why these nodes may not listen to RTS, but may listen to CTS. And that's why we are sending these control signals to try to inform as many nodes as possible that I'm trying to send. Okay? So that's another level of trying to. So the nodes that will listen to CTS will perform nav again. And then maybe some other nodes they will not listen to either, but they see the data. So when they sense, they see the data. So these also nodes will go into nav, and so on. Okay, so that's why we have different phases.
So CTS will have the time duration as well?
Yes, of course. But we'll have the time duration starting from here to here. RTS will have the time duration from here to here. So that's why the timing here is very, very, very important. Okay?
But during the SIFS, the algorithms can send, right?
SIFS?
Yeah,
No. Well, only if they did not listen to RTS and CTS, they can. Yeah, that if they listen to RTS and or CTS, okay, then they will be informed. So they should not try to access the channel. Okay? Any questions? All right? So there are different levels of avoidance.